Okay, so 0 to 2 pi goes without saying. All the choices are that. So all we need here is what is y prime squared? What is y prime? Negative sine x. Okay. So is the opposite of sine x squared? Is that negative sine squared x? So it's going to be 1 plus what? Or 1. That's the same as this, right? So answer is B. It's not going to be minus sine squared. So when you square the opposite of something, you're just going to get the same thing as if you had squared. It's the positive version of it. So the answer is going to be B. Okay, let's see what else. Any questions on that one? So it looks like 5, 6, and 7. Let's just look at those and see which one you want to do. So the number 5 is pretty straightforward, just like the one we did in class, right? It tells you're going to figure out what the spring constant is, and then we're going to figure out a little bit of work. So this is pretty straightforward. Did an example like this in class. So 6. Also similar to the example we did in class, is pulling half the rope to the top of the building half of the work. So if we're going to pull the whole amount of rope up, and then we're going to take that same rope and pull half of it up. So starting from here, is that going to be half as much work as that? Anyone try that? You just got your answer A right and just put half for answer B? I'm suspecting there were some. Okay, so it doesn't work out that way, right? It doesn't work out that way because when you pull up this first half of this rope, that's more than half of the total work you're going to do, because you're pulling up a much greater amount of rope to get it up halfway than pulling up from starting from here. So this is more than 2 times as much work as that. But just set them up as 2 separate problems, and that will prove it. Just do 2 separate problems. Here you're going to integrate from whatever 0 to 50, and here you're going to integrate from what? 25 to 50?
Yeah.
Well, not if you use the frame of reference that I told you yesterday. So if your frame of reference is this, it's not going to be 25 to 50.
Yeah, I think what it's asking for is the first half of the rope, because I did 25 to 50. And
Oh, all right, right. My bad. Okay, so exactly. I knew something was wrong. So in both cases, we're starting here. The first case, we're pulling up all the rope, and the second case, we're just going to pull up the first half of it. Well, that's gonna be more than half the work, right? So you guys were right. So this one will be 0 to 50. All right. Right, and this will be 25 to 50. That's right. Okay. Number 7. So I want to show you a different way to do this, which kind of leads into what we're going to do today. So this one is where it's hanging. The 10-foot chain is hanging. And we're going to find the work done lifting the lower end to the ceiling. So here's what the chain looks like when the whole thing's hanging down. Okay, 10 foot. and then somewhere along the way, it's like that, and then when we're done, it looks like this. Okay, so here's a different way to think about this, and this is important for where we're going. So rather than letting dx be a little change in distance, this one, we can look at this and we can say split it up into segments, maybe like a link at a time. And think about what is the weight, so what is the weight, say, of that segment? So this is a little itty-bitty segment. What is the weight or the force of one little segment? Okay, well, it's going to be, in this case, we've got 25 pounds, 10-foot chain. So what's the pounds per foot? So every foot weighs how many pounds? 2.5 pounds per foot, right? So then how much does a little bitty bit of chain weigh? If every foot is 2.5 pounds, then how much, and so this, say this, what is a little bit of chain dx? How much does that little bit of chain dx weigh? Or what's the force of gravity on that little bit of chain? 2.5 dx, right? It's going to be the pounds per foot times the number of feet. So dx is a number of feet. It's a very small number of feet times your 2.5 pounds per foot. It's going to give you the weight or the force of a little bit of chain. So here we're seeing dx has a different role. Rather than dx being moving the whole amount of chain or rope a little bit, now dx is like, okay, it's a little bit of chain, and we're going to find out, we're going to use dx to calculate the weight of that little bit of chain. That'd be 2.5 dx. You see the difference? Does that make sense? So then the question is, what is our little bit of work is going to be, or it's going to be what? It's going to be this is force times distance, right? So that little bit of chain is not going a little distance. So we can just get all the work for that little bit of chain. What distance does it go? So the distance that it's going to go is, so here's the halfway mark. It's going to go the same distance opposite of the halfway mark. So that's the distance it's going to go. So how far is it? So if we say x is the distance up from the bottom to our typical little piece of chain there, then how far is this d? How far does that little bit of chain go up there? So first then we need, how far is this? How far is it from there to the halfway point? 5 minus x. Do you see that? So what is d then? How far is that little bit of chain going to move? 2 times that 5 minus x. Do you see that? 5 minus x will take our little bit of chain to the halfway point, and then you got to do that again for its final position. So the little bit of work is the little bit of weight of the chain times the distance it's got to go. And that distance it's going to go is 2 times 5 minus x. So now we're using dx in a different way. We're using dx to mean a little bit of length of chain times 2.5 gets a little bit of the weight of the chain. And now the total distance that weight's going to move, it's going to reflect over the center point of the chain. So that's a distance of 2 times 5 minus x. So that's our force times distance. Okay, so do you follow that? Yeah.
Why'd you do 5 minus x?
Okay, because so this little bit of chain is going to go, it's basically going to go to its symmetric spot up here, right?
Yeah.
So I set my frame of reference from the bottom of the chain as x. Okay, and so then the whole chain is 10 feet long, right?
Yeah.
So how far is it from our little bit of chain to the halfway point?
Just 5.
No, from our little bit of chain to the halfway point.
Oh, that's what you did 5 minus x.
Yeah, because x is the distance up from the bottom to the chain in question. So then the distance to the halfway point is the 5 minus x, and if it's going to reflect over that halfway point, it's going to go twice that distance.
Okay.
Other questions? So then we're what? We're going to sum up all those bits of work for each little bit of chain. So down here, it's going to go all the way up here, and then right here, it's going to just go that far. But that's all taken care of in our typical bit of work. So the total work is going to be x starts at 0, right? So this is this little, they'll start with the bottom little bit of chain is at 0 until what's the last bit of chain we got to move at 5. So force times distance. Okay, anybody have a question on that? Yeah.
Why is your upper limit 5?
Because what bits of, so x is the distance up from the bottom of the chain. Which little bits of chain are we moving? So the first little bit of chain here is at x equals 0. Do you see that? Where's the last little bit of chain that we're moving when we have this configuration in the end, right? Yeah, the last little bit of chain is just the one that just moves and crosses over the center point. And that's when x is 5. But we're not moving these pieces, all this chain just never moves. There's no work that we do on the top half of the chain. All the work we do is on the bottom half of the chain to get it up there. Is that better? Yeah. Other questions? Okay, so let's try a new example here. Not working. Try this. Okay, so now today's where it gets fun. Hard and fun. Okay. Here we go. So 20 kilogram chain hangs 30 meters from the roof over the side of a tall building. Similar to what we had. Chain holds a bucket that's spilling sand at a constant rate as the bucket is raised. The initial mass of the bucket and sand is 25 kilograms. When the bucket reaches the roof, the total mass is 5 kilograms. How much work is required to pull the bucket up to the roof? So now, not only do we have the changing weight of the chain, but then we have the weight, we have the mass of the bucket, and then we have the mass of the sand that's spilling out as we raise it. Okay? So let's draw a picture. Always draw a good picture. Okay, so here's our chain. And then here's our bucket. And we're going to pull it up. And let's use our frame of reference from the top again. So this is going to be x. So what's happening here? So the mass is continually changing from the bottom to the top. So what we need is, we need mass at any value of x. If we knew the mass at any value of x, then we can figure out what the weight is and then what the work is to move it up a little bit more. Okay, so let's say let's start with when x is 30. That's when we start, right? So say down here is x equals 30. So what is the mass?
45.
And how are you getting 45?
The total number, like, we know the bucket of sand is 25 kilograms.
Mm-hmm.
The chain is 20.
Okay.
So you just add them together.
Okay. So when x is 30 meters, the mass is 45 kilograms. Okay. So if the sand is spilling at a constant rate and the chain has a constant, well, it has a its mass is constant as you go across the thing, then we can look at what happens when x is 0.
The mass is 5.
Okay, agree with that? When we get to the top, the mass is 5 kilograms. And that's because the chain, there's 0 kilograms of chain, and it's all just what's left of the bucket and the sand. So what's the idea behind we need the mass at any value of x? What's the mathematical idea? Someone else. Love the enthusiasm, but we're going to give someone else a chance.
If the sand is spilling at a constant rate, then we can divide the mass that was missed by the meters.
Okay.
So that will be 20 divided by 30.
And what would that value be? So what is that value?
That would be the rate to which the sand is spilling.
Okay, right. It's a rate of change. So she's talking about getting a rate of change of mass per your x value, right? Per your meters hanging down. Okay? And that's going to be part of this. But in general, need mass at any value of x. What kind of principle is that?
The work is going to be different at 30 meters than it will be at 25 meters because there's
Okay.
some sand that's spilling.
Right. So as soon as we start pulling it, so the work is going to continually, the force is going to change. But what is this? We need the mass at any value of x. What kind of principle or mathematical thing gives us mass at any value of x? What's that?
We need a function.
Yeah, so we need a function, right? So that's the idea. We need a function, mass as a function of x. And what do we have? And so we have what? When x is 0, m is 5. And when x is 30, m is 45. What kind of function will this be? What's that? A rate function? No, it won't be a rate function because it's going to give us mass. It's not going to give us a rate of change. It's going to give us mass. But what will the rate of change be? Yes, this is a linear function, right? So you have 2 points and you got to come up with a linear function. There are a handful of ways to do that, but it's like an algebra problem, right? So given 2 points, what's the equation of the line, or what's the function that, given any value of x, would spit out the value of m? Can you do it? You should be able to. This is Calc 2, and this is like pre-calculus. So well, everyone try that. So everyone do it. So we need some equation that's going to spit out m equals something, right, with x's. Got to have some way of doing that. Okay, anyone get it from, so Ruth or someone else has suggested that we get the rate of change, kilograms per meter. I should have gotten 4/3. Is that right?
Yeah.
Okay, so how can we go from there? We need to get m as a function of x. And we know it's a linear function. Hunter, what'd you do?
So I did m equals 4/3 x.
So that's m? M.
M equals the mass of the bucket.
Oh, okay, got it.
Yeah. 4/3.
I used capital M. So that seems like slope. Okay, so m equals 4/3 x.
Plus 5.
And how did you get that?
Because when x is 0, m is still 5 kilograms.
Okay.
So you need to add the 5 there to make that true.
Okay. And then so we can check the other point. Does the other point work? So when x is 30, do we get 45?
Yes.
Right, so you get 10 times 4 plus 5. Okay, so this one's kind of easy, because why? Because this is what? This is the y-intercept, right? One of the 2 points that you have is actually like the y-intercept of the line. And so it's like 0b, right? 0b. So mx plus b. So this is kind of an easier one when you have the y-intercept. But if you don't have the y-intercept, do you have a way of coming up with this linear function? So
Set x equal to 0.
set x equal to 0. But you don't know, I mean, how do you know what? Yeah, so tell me that.
It's like y2 or y minus like y1 equals m multiplied by x minus x1.
Okay, so here's another, this works, right? So here's your, this is a given pair. And then this is your rate of change. So there's half a dozen ways you can go about getting it, but somehow you have to have a way of getting it. So this tells us what the mass is at any value of x. So what are we going to do? We want to get a little bit of work. So when x meters is hanging over the edge, what's the little bit of work that is required to keep lifting it? So a little bit of work is force times distance. So what's the distance? Little change in x. So we're back. Now we're back to letting the little change in x be. Okay, so now here's we kind of were grappling with something at the end of class yesterday. Actually, positive x is pointing down, and which way is the bucket going? Up. So what is the distance actually? Negative delta x, because the little change is in the opposite direction of which positive x. So this is gonna settle what we were kind of struggling with at the end of class yesterday. The direction that the bucket's going is in the opposite direction of x, and so it's actually negative delta x. Okay, so what is the force? Or in other words, what's the total weight when x meters is hanging down? What's the total weight of everything we have to pull up? Right, and what's the mass, Adrian? So it's going to be the 4/3 x plus 5, that's our mass, times. So mg is F, right? This is m times g is F, times. So that's our little bit of work for x meters hanging down. So when x meters is hanging down, this is the mass of that x meters, this is the weight or the force, and then we're going to move it up a little distance. So that's our little bit of work. And then we're going to sum up all the little bits of work from what to what. So the total work will be, sum up all the bits of work, which is 4/3 x plus 5 times 9.8. And we're going to sum them up from x equal 30 to 0. So yesterday I had from 0 to 30 and I had this positive, which gives you the same number. But this actually makes more, this kind of settles why we were struggling with why is it 0 to 30 and not 30 to 0. Yeah, because we start when it's 30 and then 29, 28, 27, little by little, moving it up. But those delta x's are in the opposite direction of positive x. Sure. You're gonna plug in 0 first, and then subtract what you get with 30 plugged in. So you do the exact same thing. Do exactly what you've done with all integrals before. Just that this is a lesser number than that. Questions on this example?
If we switch 0 and 30, if we switch our places, delta x becomes positive.
Right, but that's so then if we do that, then we're saying why are we integrating from 0 to 30? Does it start at 30 and go to 0? So this is why we don't have to. This kind of settles that question.
Why aren't we accounting for the weight of the chain?
We did, didn't we?
Yes, because we include
In the mass, right? So
Oh, okay.
that's included. That's all included in this, right? So this 45 kilograms is everything: the chain, the bucket, the sand, and then this is the chain, the bucket, the sand at the top. So it's included in our mass formula. Other questions?
So why needs to linear function.
Okay, why is it linear? So there's two reasons. So what's changing? What the mass of what is changing as we lift? Two different things.
The chain.
The chain.
The weight of
So is that linear? Does the mass of the chain decrease linearly as we pull it?
Yeah.
Okay, and what else is changing?
The weight of the body. The mass.
Not the the sand changes, right? And so it says that the chain holds a bucket spilling sand at a constant rate. So because both the sand is falling out at a constant rate and the mass of the chain decreases at a constant rate, then it's a linear function. But it's a good question because in these other problems that we'll do, it won't always be a linear function. So don't just assume it's a linear function. So you have to be sure that it is to apply this technique.
Can we do an example when it's not a linear function?
Yeah, we'll have lots of examples.
It's sort of like the example we saw at the beginning, right, of the flag that he said that
Right.
when you change the hand, then it stops.
Right.
That makes it variable.
Right. So when it's not a linear function, you can't do what point slope form or y equals mx plus b. You can't use that. You need to model that function with some kind of curve, right? Some kind of curve. Okay. Other questions? So let's try that one. This is easier. This is
Honestly though, if you do physics without doing calculus, or if you're doing calculus, just not constant calculus, like once you get into slightly more difficult problems, you're calculating rates of change. Just extremely absurdly difficult issues. Calculating your rate of change, you just don't know it.
Oh, yes.
Yeah, it was. My house is right by the mountain preserve over there, so you could see the fact that like it would be raining if there wasn't so much concrete. Because like the mountain preserve, I swear to God, on the border, terrible storm on the mountain preserve, awful. Like 2 feet over where the asphalt is, no rain whatsoever. I got in my house. It rained for maybe 2 minutes. It was so dumb. I love it. I love it when it rains.
totally missed us here.
Yep.
Like, went up to the west, and then there was a part of Patch Junction. Totally missed Tempe. Sucks. It's like rain. Come on, rain.
I heard like the rain from my apartment for like 5 minutes. Just made it rain enough to make it like just a little bit.
Just you got the worst part of the rain.
Okay, so what's our mass as a function of x? Should have gotten x plus 100. Somehow, whatever way you're comfortable with. Given the points 0, 100, and 25, 125, mass is a function of x, x plus 100. So then our force is times a little change in x is our little bit of work. And so then the total work to raise the beam, x goes from 25 to 0. Or 0 to 25, and then all of that's positive.
Would we get it right on the test if we just decided to call x positive and do it 0 to 25? Or do you want it to be negative dx?
Well, if I specified the frame of reference, if I said x was this way, if I don't specify the frame of reference, then you can make the frame of reference however you want. Like you can do x down from the bottom, up from the bottom. But when you do x up from the bottom, you get a different function. You won't just get the opposite of this. You'll get a different function altogether. So if I specify the frame of reference, then there's only one right way to do it. Okay. Okay, we're going to move on to emptying tanks, unless there's a question on this one. Okay, so removing fluid from a tank. So we need some facts, first of all, here. First is the density of water. So notice these are two different kinds of density. What is this first one? This first density is based on what? Kilograms, right? So this is mass density. It's the mass per volume. Okay? This is based on what about water? Not the mass, but its weight. So this is weight density. If you're in English units, mass density will never come into play. It'll just be weight density, right? 62.5 pounds per foot cube. That's the weight density of water. Because pounds is like newtons, right? Pounds and newtons are apples to apples. They're both weight or force. So this is a weight density of water. Okay, so the total weight of an amount of water would be what? It'd be 62.5 pounds per foot cubed times whatever volume you had in feet cubed, and that would give you the total weight of water in pounds. As an example of how you use density, right? How you'd use density. If you have the volume and the density, then multiply to get the weight. Okay, so here's an example. A circular above ground pool has a diameter of 20 feet and a depth of 4 feet as filled with chocolate milk, which has a density of 64.3 pounds per foot cubed. How much work is required to remove all the chocolate milk from the pool? So, is it 64.3 pounds per foot cubed times the total volume of water in the pool? Or that would be the weight. So is this just a straightforward problem, or does it require a more pieced out approach like we've been doing? So basically, what's going on here? What's going on here? Let's understand the problem. So this is filled all the way to the top with blue chocolate milk. So in terms of let's talk about in terms of finding the amount of work to get all this milk out of the pool. What's this about? Total volume of the pool. Take the total volume of milk and times it times the density. Yes? The weight of all the chocolate milk. So that's the weight, that's the force, and work is force times distance. So what distance are we gonna multiply it by? The height. Okay, so all right, so we got 64.3 times the volume is a cylinder, right? So it's going to be pi r squared h feet cubed. And that'll be the weight in pounds. And then we're going to take that times the distance of 4 feet to get the total work.
Well, no.
You going to disagree with the rest of the class, Joseph?
Yes. Because as we change, as the depth changes going lower, the amount of work is going to change as well.
Okay.
So it wouldn't be a pure 4 feet. It would be. I need a little time to think about exactly what it'd be, but we're going to integrate the feet from 0 to 4
You agree
once
with
we find our function.
Yeah, let's get like a little change in depth, and then
Right.
we can figure out like how much the weight changes per little change in
Right.
Okay. Other comments? You understand what they're saying? Does all the chocolate milk move 4 feet to get it out of the pool? So is this, what we would do right here, would it be too much work or not enough work compared to the actual? You said not enough, you said too much.
Not too much.
Too much. Because it's assuming what? That all the milk is going to go a distance of 4 feet to get out of the pool. So it's like all that weight of milk was at the bottom of the pool. And we're going to move it the full 4 distance. But that's not what we have, right? There's milk all through the different levels, right? So instead, how do we approach this? We need something for which we can calculate an amount of work. What kind of thing is it that we're going to look at for which we can calculate an amount of work? When we look at this, what's that?
Weight at the top when it's full, and then the weight of it when it's just about done, or 0 feet, or 0.00001 feet.
Okay, but what is it? What object or what thing is it for which we're going to calculate an amount of work? What's that?
Pancake,
Tell me.
because it's a solid kind of dish. So you can calculate like over a little change in the depth, like a little sliver.
Okay.
You can calculate how much the weight has changed.
Wait, how much the weight has changed?
I'm sorry, what the work done over that little sliver was.
Yeah. So if we just have a pancake of chocolate milk, can we calculate the work to get that out of the pool? And why can we calculate the amount of work to get that out of the pool and not just the whole amount at once? how is it that we can calculate the work to get that red layer out, but we can't get all of it at the same time? What's that? No.
It's a little bit of change in it.
No.
It's a different distance, there's different work required.
So, okay.
From the top to bottom, it will take a different amount of work for each sliver of liquid,
Okay.
depending on how much there is.
So then for the red sliver, we can figure out the work because
We have a variable distance.
no, because of in the one layer. You're saying is it a variable distance?
Yeah, distance is a variable.
Why is it that we can find the work for the one layer?
It's really small.
It's because it's all at a constant distance, right? All the milk in that layer will move the same distance. So our little amount of work is going to be, it's going to be the typical work to empty one pancake or one layer. All right. And so is it going to be F times delta D or just F times D? F times D or F times delta D? Yeah, because the distance is not a small distance, right? We're going to move it, we got to get it to the top, right? When we get it to the top, then we're getting it out, essentially. So again, so we're going to we'll start with the frame of reference from the top going down like we've done before. Call that X. So X is the distance from the top of the pool down to the layer, okay? So what is the force? What is the force in question here? What's that? mg of what? Right, of that layer, right? So this is going to be mg of that layer. Right. And what's the distance going to be? It's going to be x. Okay. So what's the mass of that layer? So actually, so why is it not mg? Yeah, because we're already in pounds. So we're not going to think of it as mass times g because we're already in pounds. So we need, it's just the weight, right? It's the weight. We only use mg when we're given kilograms and we're in metric units. So it's going to be the weight times the distance it's going to move. All right, so how do we get the weight of that layer? How do we get the weight of that layer? 62.4 or 64.3. Okay. Is that the weight of it? Times the height?
Volume.
Yep, pounds per foot cubed is going to be times the volume of the sliver. And what's the volume of the sliver? Right, so it's going to be the area of the, it's going to be the volume of the cylinder, right? So that pancake is essentially a cylinder. And so the volume of that cylinder is going to be pi r squared h. What is r? Pi 10 squared times, and what's h? Delta x. So we got weight density times volume is going to give us the weight of that slice times the distance it has to go. Because it's the distance this has to go, right? The delta. So now here, the delta. This is like the Weber problem that I did. Now the delta x is part of the volume of this thing to get us the weight of it, the little change in x, and so that's going to be the weight of that layer, and then to get the work, it's the distance that we have to move that weight, and that's x. It's the distance.
That's gonna be the variable.
Yep. So each layer has to go a distance of x. If our x, our frame of reference is from the top down like that. So then the total work is going to be the work for all the layers, right? Starting at 0 until 4. So we're going to have all the layers starting at 0 down to 4, and they're going to go a distance of x, and they're going to have this weight. Okay, but?
If the point of reference is x downwards, shouldn't change of x be negative?
No, because it's not movement. This delta x is not movement. It's just an amount. It's just a height.
Oh, okay.
It's not a distance, right? This time, it's not that we're going down or going up. It's just the thickness of the layer. So the total work is going to be the sum total of the work for all the individual layers, starting at 0 and at 4, and then the weight of each layer is 64.3 pi 10 squared dx, and then that layer has a distance of x to go. Okay, anybody have a question on that?
Question?
Yeah, please. Oh, sorry.
I was wondering why the dx.
Because it's part of the volume. The volume of the layer, it has thickness, right? This is a volume of this layer. So it'd be the volume is pi r squared h. So the delta x is the h. Yeah, sure. Right, when it gets very small. Just like always before, right? Yep. So yeah, the dx is from the delta x. Other questions?
So can you think about this as like the distance we're stacking again, or no? Defining total force.
Yeah, so kind of. But now it's not just volume; it's actually work. So so before when we had pancakes, we stacked up a bunch of volumes to get total volume. Now for each one of those pancakes, we're calculating the work, and we're adding up all the work for each one, and the total work will be then the sum of all the individual amounts of work for each pancake.
Is that why the x is not 4 minus x?
So I'm defining x as if I drew x this way, then the distance, yes, if this was x, now the distance would be 4 minus x. But since I made my frame of reference down from the top layer surface of the milk, then that's the distance it has to go to get out of the pool. But right, if my frame of reference was like this, then it would be the distance each layer would have to go would be 4 minus x. Yeah. Other questions?
Sir,
Yeah,
can
please.
I understand in this way, so there are pancakes in the top, they need to move 4 feet. So the
No. There's only one pancake that has to move 4 feet. That's the one at the bottom of the pool. Every pancake has to move a different distance.
Yeah, yeah.
Okay.
So the top is in the top. So the pancake in the highest pancakes. So you need to.
So how much work does it take to get the highest pancake out of the pool?
So it's the force, the weight of the pancake
Yep.
and times 4. And then there are different pancakes, and in the bottom, the pancake just the distance they need to move is 0. So
You got it backwards. The work to get the out of to get it out of the pool, we've got to get it up to the top of the pool. That's how it's going to get out, not the bottom.
I'll move on from.
We have to move yeah. So if there was a hole in the bottom, it would be 0 work. So if we just had a hole in the bottom of the pool and just unplugged it, that'd be 0 work, because the work comes when you're moving the layers upward. You need a force to move it up. But if it just drains down, that's 0 work. There's no work to drain it out of the hole in the bottom. We've got to to get it out of the pool, we got to get it up out of the top. That means we have to lift with force. We've got to lift each layer with force up. Is it better?
Yeah.
Okay. Yeah. If there's a plug at the bottom of the pool and we just pull the plug and it all drains out, 0 work, because there's no force involved. There's distance involved, but there's no force to lift. The gravity is doing all the work for us, right? It's just letting it come out. But if we've got to lift the layers up out of the top, that's what's requiring work. Okay, so now what if there's a spout on here and all the milk has to come out through that spout, and say that spout is 2 feet. So how would it change? How would it change? Okay, so if we left the frame of reference as it is, then what would change in the integral? The distance now. Instead, every layer now has to go 2 feet further than it did before, and so the integral would change. Instead of, you'd have x plus 2. Another way to do it is make your frame of reference now at the top up there. If the frame of reference was up there, then how would the integral change? 0 to 6? Not quite. Yeah. 2 to 6. Yeah, so if your frame of reference is up here, then the layer at the top of the pool has to go a distance of how far? 2. And the layer at the bottom has to go a distance of 6. So if you could still have x here, and you could go from 2 to 6. Or 0 to 4 and x plus 2, leaving the frame of reference where it was before. Does that make sense? Any other questions on this example? Okay, so you guys try one here. So I've got a trough, okay? And here are the dimensions of the trough. At the bottom, it's 60 centimeters wide. At the top, it's 100 centimeters wide. It's 50 centimeters tall and 200 centimeters long, or deep, okay? It's half filled with water. So 25 centimeters tall, 25 centimeters tall with water. What's the work to get all the water out the top of the trough? What's the work to get all the water out the top of the trough? Okay, so you're going to have to combine some different principles here that we talked about to solve this. So I want you guys to work on this, work together.
mass density, so we need 1,000 kilograms per cubic meter. Yeah, we can do that conversion easy though. I'm just trying to think of how we do the distance. So if we take a top layer, that's going to have to travel 25 centimeters up.
You're talking about integrals way too soon here. How do we approach these problems?
Yeah, that's the little sliver that I had there.
Did you guys come up with that?
Yeah.
Rectangular?
Yeah. That's fairly certain that the height of that is. Yeah. Well, yeah. Right.
Right, because if it's not, then it's different distances.
Yeah, exactly.
That's right.
But we're stuck on the width issue.
Would you just assign that as an x rather than like a dx, or would you have to do like the width as like a certain number minus that x because the width?
We're going to integrate from what to what? We're going to. So you need a frame of reference.
We were thinking integration of from 25 to 50.
Right. That means your frame of reference for x is this way, right? That's your x, and that's fine. That's good. So now this width, what do you need? You need the width
From one side of the track to the other.
But so you want to make the width x,
It's just called y.
but we're integrating with respect to x. So this is a principle we talked about earlier in class. What do we need?
Density of
Sort of
water.
function.
What as a function of what?
We need the width as a function of x.
We need the width as a function of what your x is. And then you put your
Is 60. I have that. So. Oh, so we were talking about it at halfway. That's 8, right?
Yeah, that's what
Well,
I
we can do a point slope. So it's situation.
Yeah, we know the width. We know the width. We know the width is a function of that's this. That's the width.
I change it to meters.
meters, right? So what would it be? When x is 0.25, width is
That I have. What I don't have is this. Yes. Oh, because we're in kilograms. Yeah.
So what is that? Is that 4?
0.25 divided by 0.5.
It's change in
Oh.
change over change, right? Oh no, this isn't right. Let's do this. Do this in centimeters, it'll make it easier, and then change it at the end. X is 25. The width is 80. And when X is 50, the width is 60. So the rate of change is 20 over negative 25. Negative 4/5. So when X is 0, what is the width? Plus 1? Plus 100? So does it work? Plug in 25, you get 80. Plug in 50, you get 60. But now we want meters. So plus 1.
Yeah, we would still be. It's just because that's what we're
Delta V. Centimeters. But I changed it to meters.
And then we would see this part is not I just convert everything to meters. I was just down multiplied by gravity. Solid. Yeah, I just had to change it to me, so that's where I kind of was. That's always going to be interesting.
So x goes from what to what? Not 25 though. 0.25 to. So all this was we did in meters, right? What's that?
Why is your wafer 2 meters? Oh.
It's the length. Yeah. That's small.
It looks long, but it's not deep.
It's this wide on the top. It's not very deep. Half a meter. It's not that deep. It's pretty average trough, I think. All right, questions on this?
Yeah, how many of those do you have at home?
Yeah, no, I'm used to it. Yep.
Enough.
Even where it was in Ohio.
Can we go quickly over it?
Yeah, So I think most of us got to the point where we understood that we have to figure out every layer, the work for each layer. Because we need some kind of element for which we can calculate an amount of work. And so that has to be a horizontal layer. If it's anything but a horizontal layer, then the distance is different that the stuff has to go. So with a horizontal layer, all that stuff has to go the same distance. So we can get the work for one layer, right? So that our layers will just be rectangular solids this time. And the length is fixed, and the thickness is our delta x, but it's the width that's changing with depth. And so we need that width as a function of x. So if your frame of reference is the top of the trough, then when x is 25, the width is 80, halfway between 60 and 100. When x is 50, the bottom of the trough, the width is 60. And so from that you get negative 4/5 x plus 100. And then changing that to meters. So negative 4/5 is meters per distance per distance, right? Because it's width per depth. So this you don't have to change because it's if it's centimeters per centimeter, it's also meters per meter. Yeah.
How did you get 80?
Oh, it's halfway between, right? So if it's 100 and then 60, and we're at the halfway mark.
Okay.
So we could have done. So actually, it would have been easier to do 0, 100. So it would have been easier to do you could have had this point be 0, 100, and that would have been easier. That's actually easier. Do 0, 100, and 50, 60. But you get the same thing. And so then in meters, it's going to be negative 4/5 x plus 1 for meters. And so then our volume is going to be width times length times thickness. And the force is going to be the weight of that. So it's going to be the volume times the weight density, which is 9,800 newtons per meter cubed. And then the work is going to be the weight times the distance it has to go, which, based on the frame of reference I used, is just x. And then we're going to integrate from 0.25 to 0.5. Questions on that?
Why did it go from 100 to 1 plus 1?
What's that?
Formula? Why?
This was centimeters,
Oh, and then
and this is
okay.
meters. But this doesn't have to change because this was centimeters per centimeters. Centimeters of width per centimeters of depth. So it's going to be the same as meters per meter. So that stays the same, and then the 100. Is that a stretch or a question?
Stretch.
Okay. So just, we won't do a whole nother problem, but what if this was a circular trough instead of a trapezoidal trough? Then what would be different? So what did we do here that we're not going to do here?
The radius is going to change.
What's different then? It's a circular trough instead of a trapezoidal trough. Jacob.
You're not going to have a linear rate of change. It's going to not be constant.
Right. So you're not going to set up a linear rate of change, or a linear function between the width and the depth. Instead, your width as a function of depth will be what kind? So width as a function of x will be what? So it's not a line, right? It's not a line anymore. What is it? Isn't that quadratic? Circular. So I said it was circular, right? So if this is circular, then this function is going to relate to a function of a circle. The width is going to be what? So here we might set up something like this. We might say this is y and this is x. And you're talking about this right here is that's the x coordinate of this point, right? According to what? Okay. That's it's going to be a change in y. That's right. But this x, the width is going to be 2x, and x is going to be according to this curve. Which is x squared plus y squared equals radius squared, right? So instead of a line, you have the equation of a circle. And if you need x, you're going to solve for x. It's going to be square root of whatever the radius of the whole circle is minus y squared. And what's y? What's y? Y is your depth, right? Y is your depth. So now you have the width as a function of depth. 2 times the x coordinate expressed in terms of y, the depth. Did you catch that? So you're not going to set up a linear function. You're not going to take 2 points and set up a linear function. You're going to use the equation of a circle or make that into a function. So your width now would be 2 times x, where x is expressed in terms of y according to the equation of a circle, x squared plus y squared equals r squared.